Hello everybody. So today I have decided to talk about the common-emitter amplifier, but more specifically how to set the bias, because it's not always super clear. How do you choose the two resistors R1 and R2? So here, this is taken from a book called Practical Electronics for Inventors. I will put the title and the authors in the video info thing. But I think you have something very similar in the art of electronics. So I thought it would be a good idea to go over this thing as it relates to the biasing. So what values should you give to R1 and R2? So here, let me just increase the size of this thing so that we can see something. So that's the circuit. Very common setup. So it's a common emitter amplifier. So you have the VCC up there, R1, R2. So that's the voltage divider bias setup. So here you have the RC, so the resistance in the in the collector path, RE, the resistance in the emitter path. So this is of course the base, collector, emitter. So the input is here, so AC only, and this is the output at the collector, and you should see a voltage gain, of course. What else? Oh yes, this is an R3 and a C2 combo here. So the R3 is going to control the gain, the AC gain. Okay, so let's look at the text. Okay, so the common emitter amplifier provides voltage gain. Okay, so now he's gonna, all this talk is about figuring out what the values should be for each component. But here I'm gonna focus on R1 and R2. How do you figure out what the values should be? So here he's doing, he's setting up his sum of the unknowns. So he wants a voltage gain of -100. So this is going to be controlled by R3. So we don't need to worry about that at this point. So an F3 dB point of 100 Hertz. Again, we don't need to worry about it because this is to figure out the values for the capacitors. And this is the important one. So he's assuming that he's assuming a quiescent current IQ 1 milliamp. So IQ is IC, so it's the current that goes into the collector, which pretty much also goes into the here. So IE is about equal to IC. So that's the important part. So how does he get this value of IQ equal 1 milliamp? I'm not sure, but usually what you do is that you look at the characteristic curves of the transistor. Okay, so let's have a look at the characteristic curves. So, and you can get them from looking at the data specs of the transistor you want to work with. So, so you have axis like this, so the y-axis, but it's actually IC, so that's the collector current, and the x-axis is here, and this is VCE. 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 So they look like this. I mean, ideally, let's say I do it ideal. Okay, so there's one here, 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 and so each of these curves corresponds to a IB value. So here you have, let's say, 25 microamp, this is 50, this is 75, 100, 125, 150. This, the scale is milliamp. Oh, I forgot this one at the top. So 175. Okay, so then what you do, you're gonna draw the load line, what is called the load line. To do that, you set VCE equals 0, which means the transistor is saturated, and you compute or you measure or whatever. Let's say it's over there. So maximum collector current at saturation. So that's one point. You need another point. And the other point, you get it by setting IC equals 0, which corresponds to cutoff. And that gives you the maximum VC. So let's say it's here. Okay, so this is saturation, and this is cutoff. And now you draw that line, or you try to draw it. Okay, doing the best I can. Okay, so here it goes. So that's your load line. So this thing here is the load line. And now, so the quiescent point or the DC bias point, ideally you want it to be in the middle of that linear portion of the curve. So I don't know, let's say it's this one. Okay, because you have a lot of room for the swing of the AC, so it can go, on either side quite a bit. And what you do then, that gives you your IC and your VCE. So this is the IQ. Okay, and that's your VC here. Okay, so this is the quiescent point. Quiescent point. It's also known as the DC bias point. Okay, so let's go back to our schematics. Is assuming IQ IC equal 1 milliamp. Fair enough. So the first thing he does is choosing RC to center V out, which is equal to VC. Okay, so that's simple enough. So now he has RC. Next he selects RE to set VE equal 1 volt for temperature stability. Fine. So now he gets RE. Okay, so he has RC and RE. So now his interesting part is he has to choose R1 and R2. So you choose R1 and R2 to set the voltage divider to establish the quiescent base voltage of VB. VB equal VE plus 0.6 or 0.7. So here VB is 1.6. So he's using a VBE equal 0.6 and not 0.7. So to find the proper ratio between R1 and R2, you just use the voltage divider. Yeah, so you just do the Kirchhoff voltage law and you're all set. It's very easy to get. So you know the ratio R2 over R1. The problem is that so now you have one equation to determine R1, R2, but you are missing another equation. So let's see what he says. So this means that R1 equal 11.5 times R2. So now he needs another equation. And what he's saying is that R1 in parallel with R2 should be basically much less than the resistance when looking into the base of the transistor. The DC resistance looking into the base. What's here? So it's the resistance looking into the base going this way. Okay, the DC resistance. Okay, so what he's going to say that R1 in parallel with R2 is equal to 1/10 of R in base DC, and that gives you the two equations, and from those two equations you get R1 and R2. Okay, so that's the problem. Is that how do you get this thing? Where does this come from? Okay, where does this come from? So we're going to look into that. Okay, so to understand what's going on, you really need to write down the equations, otherwise it gets really hard to figure it out. So fortunately there's a professor at GIT, that name is Marshall Leach, that wrote this nice PDF that explains not everything, but is very handy and very practical, because you can have any bias setup. It can be quite complicated, and with this you can figure out what's going on. So here you have your transistor with the collector, base, emitter, and at each lead you consider the Thevenin equivalent circuit. So you have here, so this is the he's calling it VCC, so this is the V Thevenin for the collector, RCC the Thevenin resistance, same thing for the base and same thing for the emitter. Notice the notation he's using. So he's using double C, double B, so that you don't confuse it with the VB here, or the VC or the VE. And of course this is the VBE, the junction, 0.6, 0.7 volts. So the math is actually very easy here. Okay, so here this is you apply Kirchhoff voltage law. Here you use the relation IC equal beta IB equal alpha IE, alpha equal 1, and this is the transistor gain, and you solve for IC, which is the important variable here. So you get this equation. IC equal VBB minus VEE minus VBE. VBE is equal to 0.6 or 0.7. RBB divided by beta plus REE divided by alpha. Alpha equal 1, so it's just plus REE. But, okay, so that's the equation. Now what he's doing is that he's taking an example which is exactly the setup we have. Okay, exactly the setup we have. So we have the resistance in the collector, resistance in the emitter, and you have your voltage divider. And here is more general, is using a V plus. So this is a potential V plus, and here the potential is V minus. In our case, V minus is 0 and V plus is the VCC. But okay, so this is more general, so we're going to use that. Okay, so now let's go back to the equations. So in this case, the VBB is equal to V plus R2 plus V minus R1 divided by R1 plus R2. RBB is R1 in parallel with R2. VEE is equal V minus, REE equal RE, VCC V plus, RCC equal RC. Okay, so that's one example, but he has many other examples where you have much more complex configuration, but you can figure it out the IC the exact same way. Okay, so he's got, I mean, look at this one. Okay, so let's go back. So now we need to write IC using those values. So in our case, IC is equal to, so VBB, so V plus is VCC, so it's gonna be, hold on, so V plus is VCC, so here I'm writing VBB, so it's gonna be VCC times R2 plus nothing, because V minus is 0, and you divide by R1 plus R2. Okay, so that's the VBB. Then you have the minus VEE, which is V minus, that's going to be 0, minus VBE, which is 0.6 or 0.7 volt. Then the RBB over beta, so RBB is R1 in parallel with R2 divided by beta plus REE is just RE. Okay, so it shows that for IC to be stable and not dependent too much on beta, you want, and the only term that depends on beta is here. Okay, so you want basically this term RE to be large compared to R1 in parallel with R2 divided by beta. So you want R1 in parallel with R2 divided by beta to be small when compared to RE. Okay? In other words, you want R1 in parallel with R2 to be much less than beta RE. So basically in reality you would say R1 parallel R2 should be less than 1/10 beta RE. And if you go back to the schematics and the explanation about how to choose R1, R2 in the book, it's exactly that they use. Okay, so that's where it comes from. R1 in parallel with R2 must be less than 1/10 of beta RE. Okay, now you may ask, how do you get the VBB and the RBB. So let's look into that. Let me get rid of this now. Okay, so let's move on to that. So we want to figure out how to get VBB and RBB, which is the Thevenin voltage and the Thevenin resistance in this circuit. Okay, so let's figure out how to compute VBB. First, I need to redraw this thing. So here you have R1. Here you have R2, and here you have the base. I'm not going to draw anything else because we don't need anything else. Okay, now on this side at least. Now let's do like voltage source. So plus, minus, so that's V plus. And let's connect that to ground. Same thing on the side. So let's put a plus, minus, so that's V minus, which could be positive, by the way. And connect that to ground. So those two grounds are connected. So when you do the equivalent, the Thevenin equivalent circuit, what are the nodes that you consider? You consider, well, you have two choices really. You can consider, okay, so there are two choices. We can go this way, this node, and that node, the ground here. Okay, so now we have to compute the VBB. So those two are the Thevenin nodes. So let's compute VBB. So VBB is this voltage. VBB. So it's a voltage divider. So VBB minus B minus is equal to, so VBB minus V minus is here. Okay, so it's equal to R2, so that's voltage divider, R2 divided by R1 plus R2 times this voltage. So this voltage is what? It's V plus minus V minus. Okay, so now if you bring B minus on the other side, you get VBB equal V minus R1 plus V plus R2 divided by R1 plus R2. Okay. Now you could have computed the VBB in a different way. So let me erase some stuff here. Well, that we can erase, doesn't matter. This. Get rid of this. Okay, so let's put back the ground here. So instead of taking those two nodes, you could have taken this node and that node for your Thevenin equivalent circuit. And so exactly the same as that one, except that now it's VBB. It's the same idea. VBB minus V plus is equal to R1 over R1 plus R2 times, so now it's inverted, so it's going to be V minus 1, V minus V plus, and this gives you, if you put V plus on the other side, this gives you exactly the same thing, V minus R1 plus V plus R2 divided, oops, let's be nice and clean here, divided by R1 plus R2. So which is what Mr. Marshall Leach wrote. So that's exactly the same. Okay, so let's move on. Now we need to see how we compute the RBB. Okay, so let me put back transistor. So what you do, so okay, so I'm here. What you do is that you short any source. So this gets shorted. Okay, the other one, same thing. So that gets shorted. Okay. So now you have to compute the resistance between this point and that point. But remember that this is ground, so it's actually R1 in parallel with R2. Okay, so this guy goes here. Okay, so I'm back in the book. And okay, so this is R1 in parallel with R2 must be less than 1/10 of R in base DC, and R in base DC is HFE, which is the beta, times RE, which is exactly what we derived previously. Okay, so basically now you have the two equations, and you can find R1 and R2 for the voltage divider. Okay, so here for completeness, I'm just going to show the rest, what's in the book. But I'm not going to comment on it, I'm just going to show you. So yeah, so you have a certain gain you want, so you choose the R3 based on that. So that's the formula. Then he computes the C1, the filter, and then he computes C2. so both filters, and that's it. And you have, and if we go back, it shows the circuit with all the values. Okay, but as I said before, here I was only focusing on the R1 and R2. Okay, so I'm gonna stop here. I'm gonna put the link to that PDF by Marshall Leach, and I highly recommend you take a look at it. All right, so if you like this kind of comment, please like, comment, subscribe, and I will make more. Bye.